Welcome to the first in a series of boring videos about chemistry where I'm simply going to be reading my notes to you and explaining what's going on in the class. So we're going to start with chapter 14 in your book, Solutions and Their Behavior. Recall probably from Gen Chem 1 that a solution has a solvent and a solute. The solution is a homogeneous mixture of two or more substances in a single phase. So when we're dealing with solutions, we're talking about a liquid dissolved in a liquid, a solid dissolved in a liquid, a gas dissolved in a liquid, a gas dissolved in a gas. It's got to be a homogeneous mixture, not heterogeneous where you can see the particles, but a homogeneous mixture. And the solvent is the thing you have more of, and the solute is the thing you have less of. We're going to start with the solutions, what goes into making them, and some of the terminology and the energetics of that. And then we'll end this chapter with colligative properties. These are properties that are based on the number of solute particles, the number of things you have dissolved in your solution, not necessarily what those things are, just the number of particles dissolved. And in your book, we're going to skip over this units of concentration. We'll come back to that in the next video. But for now, we're going to go straight into the solution process and entropy. And we're going to start with entropy here. Entropy is a new term. You may not have heard of it. Entropy has to do with, for lack of better terminology, randomness, how random things are. Because it turns out in nature, the more random things are, the more nature likes that. And it's due to energy. The more you can disperse energy through a system, the more nature likes that. If you have, for example, a piece of metal, if you heat up one end of the metal, that heat doesn't stay in that end of the metal. That heat propagates down through that piece of metal till the whole piece of metal is hotter because the energy is dispersed that way. Nature just likes to disperse the energy. And it turns out the more a solute, the more it is mixed in with a solvent, the more spread out the molecules are, the more spread out the energy is. And so things just want to mix. For example, if you have two gases, this gas with the black dots here with the red dots here, and they're separated by a barrier, if you were to remove this barrier, those two gases will mix randomly with each other. And that's due to entropy. Having them more random, having the molecules spread out and mixed more evenly is going to be the way nature wants it to be. That's just going to happen spontaneously. Likewise, if you dissolve salt, sodium chloride, in water, the sodium chloride doesn't stay in one spot. It dissolves evenly throughout the water. So that's entropy, and it's going to drive a lot of our mixing here. All right, so let's also look at here, number one, the saturated solution. A saturated solution means no more solute will dissolve in that solvent. But let's look at what's really going on. For example, if you have CuCl2, copper 2 chloride, it's a solid. You can dissolve that in water. It will dissolve in water. But you add a little copper 2 chloride, it'll dissolve, add a little more, it'll dissolve, add a little more, it'll dissolve. Eventually, no more will dissolve. Once no more copper 2 chloride will dissolve, we've reached the saturation point. You have a saturated solution. Now, how do you know you have a saturated solution? Usually because you've got a little bit in the bottom that won't dissolve anymore. So you have a little bit of solid that stays, it won't dissolve. And that's what it looks like on the macroscopic scale. If you're looking at it, it appears, okay, no matter how much you stir, you have this solid that is sitting there and it's not dissolving. However, if you looked at the microscopic scale, if you looked what was really happening down at the molecular level, you would see that some of this copper 2 chloride is dissolving. But at the same rate that some of this copper 2 chloride dissolves, some dissolved copper 2 chloride is precipitating out of the solution to form a solid. You have a dynamic equilibrium process here. So when you mix copper 2 chloride or any salt in a solvent such as water, and you mix it and mix it and mix it, and you see no more is dissolving, the truth is, yes, some of the solid is dissolving into its ions, but at the exact same rate, some of these ions are getting back together and reforming the solid. You have this dynamic equilibrium here. And we are going to spend most of this semester discussing equilibrium. So knowing equilibrium is a very good thing. If you really understand and get the gist of equilibrium, you are going to do much better this semester. Learn to love equilibrium. Okay. So it turns out different molecules, different ionic compounds, have different solubilities in the solvent, and normally in this class our solvent is going to be water. And the solubility, some things like sodium chloride, you can dissolve a whole lot of sodium chloride in water. Sugar does not dissolve as well in water. Sugar has a lower solubility in water. You will get to the saturation point of sugar in water at a much less amount of sugar compared to salt. And so let's look at this. The solubility, for example, of copper 2 chloride is 70.6 grams per 100 milliliters of water, meaning simply you take 100 milliliters of water at 0 degrees Celsius. Make sure it's the liquid water at 0, not ice. You have 100 milliliters of water at 0 degrees Celsius. You can dissolve 70.6 grams of the copper 2 chloride in there. That is its solubility. That is where you've reached a saturated solution. So, question, what would happen if we put 150.0 grams of copper 2 chloride in 200 milliliters of water? Well, hopefully you can see that the solubility is 70.6 grams per 100 milliliters of water. So if we have 200 milliliters of water here, that means we should be able to dissolve twice the amount of copper 2 chloride. If we have twice the amount of water, we should be able to dissolve twice the amount of copper 2 chloride. So we would predict that if we had 200 milliliters of water, you should be able to dissolve 141.2 grams of your copper 2 chloride, because 100 milliliters of water would dissolve 70.6. Twice 70.6 is 141.2. So what would happen if we had 150 grams of copper 2 chloride? 200 milliliters of water, 141.2 grams of the copper 2 chloride will dissolve, leaving 8.8 grams of the solid behind. And that 8.8 grams of solid behind will be constant. It'll stay at 8.8 grams. However, if you looked at the individual molecules, some of this 8.8 grams of copper 2 chloride is dissolving at the same rate. Some of the dissolved copper 2 chloride is coming back out. So the amount will always remain 8.8 grams, even not dissolved, even though this equilibrium is happening. Okay. So now let's look at liquids dissolved in liquids. If two liquids mix to an appreciable extent in all their proportions, for example, if you have water and methanol, methanol is an alcohol. If you have water and methanol, it turns out if you have a 50-50 mixture of water and methanol, they are completely miscible. They mix together, not a problem. If you had 5 milliliters of water and 95 milliliters of methanol, much more methanol, the methanol would be the solvent in this case, that water will dissolve in that methanol. That 5 milliliters of water will dissolve in 95 milliliters of methanol, no problem. If you had 5 milliliters of methanol and 95 milliliters of water, that water will dissolve in the methanol. It doesn't matter what the proportions of water and methanol, any amount of methanol will dissolve in water, any amount of water will dissolve in methanol. They are miscible. If they were immiscible, that means they would separate into two layers. because they wouldn't dissolve in each other. One of the liquids would be more dense, would be the bottom layer. The other liquid, less dense, would be the top layer. And this miscibility is determined by the like dissolves like rule. It's not really a rule, just a phrase, like dissolves like. And recall, like dissolves like is all about polarity. If you have two polar liquids, they are miscible in each other. Two things that are both polar are miscible. Two things that are nonpolar are miscible. A nonpolar solute and a nonpolar solvent will, if they're both liquids, will be miscible due to their intermolecular forces, which we're about to discuss. Which means if you had a polar liquid and tried to mix it with a nonpolar liquid, they would be immiscible and would separate into two layers. For example, CCl4, carbon tetrachloride, and C8H18, the organic molecule octane. If you did the Lewis structure for CCl4, you would find that it's tetrahedral and all of the individual bond dipole moments cancel each other out. Therefore, CCl4 is nonpolar. No dipole-dipole forces here. All of our organic molecules that are just carbons and hydrogens are also nonpolar. Our hydrocarbons are nonpolar. So we have two nonpolar molecules. We'd expect two nonpolar molecules to be miscible with each other. Since they're both nonpolar, the only intermolecular forces that are involved are dispersion forces. And it turns out the dispersion forces are very similar between these two molecules. Between any two nonpolar molecules, you'll usually have very similar dispersion forces. Meaning, if you have a bunch of carbon tetrachloride, you have one carbon tetrachloride strongly attached to the other carbon tetrachloride through the dispersion forces. Recall, dispersion forces aren't all that strong. The deal is, if you have a bunch of C8H18s and they are attracted to each other through dispersion forces, if you mix those two, the energy required to break the carbon tetrachloride dispersion force attraction to the other carbon tetrachloride is the same energy you would get back when a carbon tetrachloride interacts with a C8H18. And since these are energy terms, stabilities, this is all enthalpy delta H. So, breaking the attraction between carbon tetrachlorides takes a little bit of energy. However, you get all that energy back, pretty much the same energy back when you attract the carbon tetrachloride to the C8H18. So by mixing these two molecules, there's no energetically favorable anything in terms of heat. However, when you do mix these, when the carbon tetrachlorides and the octanes are completely mixed together, the solution has less order to it. The energies can be spread out. Therefore, the mixture has more entropy, and that's what will drive this mixing process. The less ordered system is the way nature likes it, and so these two molecules are miscible with each other, will spread out evenly in each other due to entropy, because the delta H term enthalpy, the heat and stability is the same for carbon tetrachloride reacting with carbon tetrachloride attracted to carbon tetrachloride is the same amount, roughly the same amount of traction to octane. And so that's what we have with liquids dissolved in liquids. If you have solids dissolving in liquids, that still follows the like dissolves like rule. Nonpolar solutes will dissolve in nonpolar solvents. More polar solutes, more polar solids will dissolve, such as sugar, will dissolve in water, a very polar molecule. Ionic compounds, well, things get interesting with ionic compounds. Ionic compounds do not dissolve in nonpolar solvents. For example, sodium chloride, the ionic compound, will not dissolve in octane, a nonpolar liquid solvent. However, when we look at ionic compounds dissolving in water, one would think that ionic compounds should dissolve in water really nicely. Many ionic compounds, such as sodium chloride, do dissolve in water. However, other ionic compounds do not dissolve in water. And it's actually not the easiest thing to predict, so instead of trying to predict what's going to go on, we came up with our solubility rules. Remember that from Gen Chem 1, all our solubility rules? That whole table of solubility rules is due to the fact that when you have ionic compounds, you have to follow these rules to see if they'll dissolve in water, because like dissolves like just isn't applying very well. Sodium chloride dissolves in water really nicely. Silver chloride does not dissolve in water, even though silver chloride is an ionic compound. So we just have to memorize those rules for ionic compounds dissolved in water. All right, I'm going to stop this video here, and in the next video we'll start looking at the enthalpies of solution.